principles of convection. So, if you're a first-year chemical engineering student, you might be wondering, why do we even care about fluid flow when we're just trying to calculate heat? Well, it turns out, for convection, it's everything. To really predict that heat transfer coefficient, the number that tells us how well heat is moving, we've got to analyze how the fluid's movement stirs up the temperature right at a surface. Okay, first up is the boundary layer. Just think of it as this super thin, sticky zone right on the surface of an object. In this layer, the fluid's own internal friction, its viscosity, slows everything way, way down, almost to a complete stop right at the wall. And this tiny region is a huge deal, because it's basically the main bottleneck for heat trying to get through. Second, how do we even know what the flow is doing? That's where the Reynolds number comes in. It's kind of like a cheat code that tells you if your flow is smooth and orderly, that's laminar, or if it's a chaotic, churning mess, which we call turbulent. Turbulent flow is way better at mixing heat. But, and this is important, there's still a tiny, quiet sublayer right at the surface that ultimately controls things. And finally, you need the fundamental dynamic equations to tie it all together. See, far away from the surface, we can often get by with the simpler Bernoulli equation to relate pressure and velocity. But to see the whole picture, especially with really fast or compressible flows, you have to bring out the big guns, the full conservation of energy equations. So, when you get these three things, the boundary layer, the flow type, and the conservation laws, you can see exactly how a fluid's physical motion is directly linked to heat transfer. Let's dive into more detail.
Let's talk about convection. And I know that might sound like something straight out of a physics textbook, but stick with me, because this is actually a story about the hidden drama of how fluids flow all around us every single day. All right, let's start with a little riddle. What could a nice, cool breeze possibly have in common with the inside of a scorching, hot car engine? I mean, think about it. One is this wonderful, gentle feeling, and the other is basically a controlled explosion keeping metal from melting. They seem like total opposites, don't they? Well, the wild thing is, the secret that connects them is exactly the same. If you really want to get how convection works, the science of heating and cooling, you first have to understand the story of how fluids, things like air and water, actually get from one place to another. Okay, so every story needs a setting, right? And for this story, all the action starts in what we'll call the zone of influence. This is the stage. It's where the fluid first meets a surface, and everything starts to happen. So picture air flowing over something flat, like an airplane wing. The very instant that air touches the wing, a special region forms right there on the surface. And in this zone, the fluid gets slowed down a lot because of friction. And this super important area? That's what we call the boundary layer. So what's causing all this friction? Well, it's a property that all fluids have called viscosity. And honestly, the easiest way to think about viscosity is just as a fluid's internal stickiness. It's that drag force between all the little layers of the fluid as they're trying to slide past each other. On one end of the spectrum, you have low viscosity fluids. Think about air or water. They flow super easily, not a lot of resistance. But on the other end, you've got high viscosity stuff like honey or motor oil. They're thick, they're sticky, and they really resist flowing. This stickiness is a huge part of our fluid's character. Okay, so our fluid is in the boundary layer, dealing with its own stickiness. And this is where the plot really thickens. Because it turns out our fluid can have two totally different personalities. No, seriously, depending on the conditions inside this one little layer, the flow can be beautifully smooth and orderly, or it can just go completely wild and chaotic. First up, you've got laminar flow. Picture perfect, smooth layers just sliding past each other. It's elegant, it's predictable. And then you have turbulent flow. This is chaos. The source material calls it a random churning action. It's a mess of irregular eddies and swirls. All that churning means the fluid is mixing like crazy, and that changes everything. So, our fluid is at a crossroads. It can take the calm, laminar path, or it can take the wild, turbulent one. But what decides which path it takes? Well, that brings us to the tipping point. So, what is it? What's the deciding factor between that smooth, orderly flow and the wild, chaotic stuff? It might look random, but trust me, there is a very specific trigger that forces the choice. And the answer is this incredibly elegant concept called the Reynolds number. The best way to think of it is as a flow character score. It's just one number, and it combines everything: the fluid's speed, its stickiness, the size of the object, and it spits out a prediction of exactly what kind of personality the flow is going to have. So what's the magic score we're looking for? Well, when we're talking about a fluid flowing over a flat plate, that critical tipping point is generally agreed to be a Reynolds number of about 500,000. See, if you're below that number, everything's stable, the flow is laminar. Any little bumps in the road just get smoothed out by the fluid's own stickiness. But the moment you cross that threshold, those same tiny disturbances don't get smoothed out anymore. They get amplified, they grow, and bam, the flow flips from smooth to totally turbulent. All right, let's recap. We've got two types of flow: calm or chaotic. And we've got the Reynolds number that tells us which one we're going to get. But what on earth does any of this have to do with our original question about cool breezes and hot engines? Let's bring it all home and talk about why chaos moves heat. The whole secret is in the mixing. In that nice, smooth, laminar flow, heat has to pass really slowly from one molecule to its neighbor. It's not very efficient. But in turbulent flow, oh man, you have these big old chunks of fluid physically moving around, carrying huge amounts of energy with them. It's just way, way more effective at transport. And I'm not talking about a small difference here. It is absolutely dramatic. The amount of heat that smooth, laminar flow can transfer, it's fine. It's pretty low. But for turbulent flow, it's off the charts. That random churning chaos makes a massive difference. So it all comes down to this. When your goal is to move a lot of heat and move it quickly, whether you're cooling a car engine or heating up a room, that wild, chaotic, turbulent flow is your best friend. In the world of heat transfer, chaos is very often king. And this leaves us with one last thing to think about. If turbulent flow is so fantastic at moving heat, can you think of any situations where an engineer would do everything they could to avoid it, where they'd actually fight against the chaos to keep the flow as smooth and laminar as possible? I'll leave you with that one to chew on. Thanks for tuning in.